Hello. So far we've discussed techniques for showing invalidity in predicate logic, but we still haven't learned how to prove that a PL argument is valid. In this video we're going to remedy that by introducing a natural deduction system for PL. Not all the elements of this system are new though, since this is just an extension of the system we use for sentential logic. So, like the previous one, this is going to be a set of truth-preserving rules which will allow us to construct derivations, including subderivations, from premises or assumptions to conclusions. Likewise, we'll have basic and derived rules, and these basic rules will be comprised of introduction and elimination rules, a pair of them for each of the operators in the language. And here comes a novelty. We have two new operators, which are the universal and the existential quantifier, respectively. And each of them will have its own introduction and elimination rule. In this video, we'll start with the two simpler ones, which are universal elimination and existential introduction. Let's start with universal elimination. This is a very intuitive rule. This is the rule that allows you to go from the premise that everything will disappear to the conclusion that this desk will disappear, or that I will disappear, or that the earth will disappear, and so on for everything in our universe of discourse. In terms of predicate logic, if you have a universally quantified sentence like, for every x, x is f, and if your domain contains these individuals, then you're entitled to infer the truth of all these sentences. That is, you're entitled to infer the truth of all of its substitution instances in the domain in question. And that's all there is to it. Really, nothing more. But to put it in official terms, the universal elimination rule is the following. If x is a universally quantified sentence, then you are licensed to conclude any of its substitution instances below. Notice that for the previous examples to work, we have to make an assumption. The assumption that is built into this system is that we're always dealing with a non-empty domain. This means that our domain will always contain at least one object, and so our names will always refer to something within the domain. There are other logical systems that drop this assumption, but we'll leave it in place for the rest of this course. Okay, here are some examples of universal elimination. This is a perfectly good derivation. You begin with every x is f as the premise, and then conclude fa by universal elimination from line 1. Likewise, suppose we start from this premise, and this sentence is one of its substitution instances. Then in the next line, we're going to have this sentence as our conclusion. As I said, this is all there is to it. This is the simplest of all the new rules. Okay, now to the next. Existential introduction. Existential introduction is what allows you to go from a premise such as Al loves Beth to an existentially quantified conclusion such as someone loves Beth. And from this second sentence to the conclusion that someone loves someone. The mechanics of this rule have to do with the replacement of names with existential quantifiers and variables. This is a formal syntactic process called existential generalization. And so, before we introduce our rule in its full glory, we need to define this notion. So, suppose that you have a sentence X containing the name S. Then, to get an existential generalization of sentence X with respect to name S, we need to do three things. First, delete any number of occurrences of S in X. And this is very important. It could be 0 occurrences, 1 occurrence, 2 occurrences, and so on to n, where n is the total number of occurrences of the name S in X. Second, we replace all the occurrences of S we deleted with a single variable, u, which is free in those places where we are introducing it. And last, we add an existential quantifier followed by the variable we are introducing. Here are some examples. Let's get an existential generalization of HA. Then, the first thing to do is to replace 0 or more occurrences of the name A with a variable. Here we replace 1 occurrence of A, and we use X as the variable. Last, we place an existential quantifier at the front, with the same variable we introduced in the last step, so as to bind the variable. Here's another example. Let's give an existential generalization of this sentence. In this case, and for no reason at all, I'm just going to replace 1 occurrence of the name A. And that occurrence is the first from left to right. Here's a tip. Whenever you're introducing a variable in a situation like this, use a variable that isn't currently in use. That will save you a lot of headaches. So here I use y because x is already present in the sentence. And the next step is to insert the existential quantifier, followed by y, the variable I just introduced, and which is now bound by the quantifier in question. Also, don't forget to enclose the whole sentence to the right of the quantifier in parentheses. Here it doesn't really matter, but if I had decided instead to generalize on the last occurrence of A, then I would definitely need the scope of the quantifier to be extended to the end. Otherwise, I would end up with an open sentence. In fact, let's do it. Let's generalize on both occurrences of A. So we replace both the first and second occurrences of A with y, and then introduce the quantifier variable pair, along with a couple of parentheses that allow the quantifier to bind the rightmost occurrence of y. Keep in mind that our definition says that the variables we introduce must be free where they occur. If I try to substitute a's with x's, then the third occurrence of x would not be free, and so it wouldn't be a legitimate target for existential generalization. That's why it's a good idea to always introduce new variables. Also, notice that the notion of existential generalization is in some respects the converse of the notion of substitution instance. In the first place, instantiation proceeds downward, from quantified sentences to sentences with names, whereas generalization proceeds upward, from sentences with names to existentially quantified sentences with variables. In a substitution instance, you replace variables with names, but in an existential generalization, you replace names with variables. In a substitution instance, you get rid of a quantifier, but in an existential generalization, you introduce a quantifier. Here, the quantifier has to be existential, but there's also a pure notion of generalization that can happen with either quantifier. After all, these are purely syntactic notions. And this is important, when you're doing a substitution instance, as when you apply universal elimination, once you eliminate the quantifier, you must replace all freed occurrences of the variable with the same name. However, with existential generalization, you can replace any number of occurrences of a name with a variable. You don't have to replace them all. Okay, now that we are experts on existential generalization, let's define the rule of existential quantifier introduction. The rule goes like this. If x is a sentence, then you are licensed to infer an existential generalization of x anywhere below. And that's all. Here's an example. Suppose that you have A is f as a premise. Then, to apply existential introduction, you need to substitute a variable for the name and head the whole thing with a quantifier, like this. And so there is an x such that it is an f can be inferred from fa by existential introduction on line 1. Now let's start with this premise and apply existential introduction. Let's move the derivation to the right side of the screen and use the left side to showcase the existential generalization operations. Okay? So we're going to use x as a variable, and we're going to generalize on the first two occurrences of b. Here we replace the first occurrence of b, and now the second. The last step is to introduce the quantifier and the parentheses. And then our existential generalization can be line 2 of our derivation, by existential introduction on 1. You can apply existential introduction twice in a row, or 3 times, or however many times you need. Thus, from the fact that A, B, and C stand in the relation R, you can immediately infer that there is an x that stands in the relation R to A and B, and from this that there is an x and there is a y that stand in the relation R to A. And this in its turn allows you to conclude that there is an x, y, and z that stand in the relation R. Now let's do a couple of examples combining the rules we have so far. Show that this argument is valid. We number our premises and write our intended conclusion on one side. Then we explode the universal in line 1 to get if fa, then ga. Now we explain the universal, again, this time on line 2, to get the antecedent of the conditional. Then we detach ga by conditional elimination. And in the end, we obtain our conclusion by existential introduction on line 5. Here's another example. Here are the premises, and that's the conclusion. Now clearly, since our conclusion occurs as the consequent of the conditional in line 1, our subgoal is going to be to get there is an x such that it is t, so as to be able to use conditional elimination, and this is where we're heading. We exploit the universal on 2 to get the conjunction ta and ma. Then we get TA by ampersand elimination. We get there is an XTX by existential introduction. And now we have a match for the antecedent of the conditional in line 1. And so we detach the antecedent and we get our conclusion. Okay, this is all for this video. Goodbye.